Hello, my name is Vincent. Today I'll be demonstrating how we can interact with our documents using large language models on the Nutanix Cloud Platform. The Nutanix Cloud Platform that I'm using today for this demonstration is fully hosted on premises in a data center. This means that all the large language models, APIs, and vector databases that we are working with are all hosted on premise. The benefit of this is that when everything is running on premise, organizations now have control over their data without having to send or rely on public APIs in order to reap the benefits of large language models in their organization. This is a front-end web UI that I have built over the weekend as a project to get familiar with large language models using LangChain, Milvus, Nix.js, and FastAPI. Now I will be uploading a user guide on the Nutanix Kubernetes Engine so that I can interact and ask questions about the document later. Once the document has been successfully uploaded and processed as shown in our interface, we can then go ahead and ask questions about this document. One of the most recent questions that I had was how do we rotate certificates for a Nutanix Kubernetes Engine cluster? So I'll just go ahead and ask that. Rotate certificates, initiate certificate rotation by running the following command. So as we can see from the response and compare it with the actual document, it seems to be quite accurate. Now this is a simplistic demo, but it shows you the power of what can be achieved even with open source large language models and 2 days of development efforts. Now let's go through what happens under the hood. So the Nutanix Cloud Platform is made up of 3 physical servers, or a collection of physical servers. In this diagram, I have got 3 physical servers labeled Node 1, Node 2, and Node 3. Each of these physical servers has a NVIDIA P40 GPU installed. A Nutanix cluster is then created using these physical servers in order to create a platform that is suitable for running large language model applications. Some of the services that the Nutanix Cloud Platform provides is a Kubernetes engine to run containers in a scalable and resilient fashion, GPU capabilities to help accelerate inference and training, persistent container storage for our vector database as well as document storage, a database as a service for copy data management, and lifecycle management of SQL or NoSQL databases. And lastly, an object store for storing large amounts of unstructured data such as document, text, images, or videos, which can be used for inference or training. We then deploy a Kubernetes cluster using the Nutanix Kubernetes Engine, which manages the lifecycle of Kubernetes such as scaling, creation, and upgrades. We can also pass through the P40 GPUs to the Kubernetes cluster to help accelerate inference. So on the Kubernetes cluster, we deploy our LLM applications and vector database. There is a front end that is built using Nix.js and Tailwind CSS. The backend is built using Python, LangChain, and FastAPI. We are also using GPTQ for quantized models. This allows us to load a 13 billion parameter model into the P40 GPUs, which has a limited amount of RAM, and also helps us in inferencing speeds. Now let's run through some of the process of what I have done earlier. So earlier what I've done was I actually uploaded a PDF, and what this does is that I actually interacted with the front end, which then routes me to the /upload route, which then uploads the PDF. So this PDF then gets processed by the LangChain's PDF miner loader, which then outputs a text extracted version of a document from the PDF. Now, because this document is extremely huge and our maximum context length or token length for the large language model that we're using is 2048 tokens, we need to actually split it into smaller text chunks. So we are using the LangChain's recursive text splitter to actually split it into multiple individual chunks. So once we get this text chunks, what we are going to do is we are going to send it over to the LangChain's Hugging Face instruct embeddings, and the model we are going to be using is the Hong Kong University natural language instructor XL model. This model is also loaded into the device, which is CUDA 0, which is my GPU. So once this is done, we then send the embeddings into the LangChain Milvus connector, as well as documents to actually store the embeddings and documents. So once this is done, the application has now processed and uploaded the documents. The next thing that we can do is a query. So a query is then sent to the LLM front end, right? Which we then pass it over into the query route on the backend server. So the backend server then takes this query and sends it over into the LangChain Hugging Face instruct embeddings to actually generate the query embeddings. What this does is that it creates some embeddings so that the LangChain Milvus retriever can actually use those embeddings to perform a similarity search. So what happens then is we retrieve the top 3 document chunks using similarity search to the Milvus retriever. We then get 3 chunks from a document. What we then do is we send it over into the LangChain retrieval Q&A chain, which interfaces with the Hugging Face pipeline, which uses the Manticore-13 billion parameter GPTQ model. The model then extracts out the response and pass it over to the front end. Right, so now that we have got the process flow covered, we can actually take a look at the code. So this code is currently hosted on GitHub. I will have a link in the description. So everything runs within, from the backend perspective, everything runs in Python and it's hosted in backend.py. Right, so these are the imports that I have used. I've got AutoGPTQ, and also we need to build from source and install. Right, so we can actually do a git clone and a pip install in order to perform the installation. We then instantiate the application using Fast API. We need to perform some CORS configuration, right? Because especially if you're using it in development environment. But if you're doing it in a production, then we have to definitely set the origins and methods and headers properly, right? So on startup, this is essentially when the application first starts up, right? So we need to go and load some variables, get the environment variables from and store it in a variable. What we then do is to check whether CUDA is available on the worker node or on the container. Then we then instantiate the model. The tokenizer is then also used using the same 13 billion Manticore model. Then we instantiate a pipeline, and we ensure that the first piece of text is generated from the model before we actually go past the startup phase, right? We also need to load the instructor embedding so that we can perform embeddings, and it's all cached within the system, the GPUs itself. So there are 4 routes rather. The first one is if you hit the root directory, then it just returns a status ready. The post /upload route was the route that I mentioned earlier, whereby we can upload a PDF file. It actually loads a PDF file using the PDF miner loader. It uses the recursive stack splitter to split the documents, then sends the embeddings over into the Milvus database. For query, it's very, very simple. It's we are setting the Milvus database as a retriever with a k is to 3. This means that we'll return the top 3 documents that has got the same similarity. Then feed those documents into the retrieval QA chain using the Hugging Face pipeline of the generate text that we have specified earlier. Then it just returns a response. And a test query is something that I just embedded but not published on the front end. So how do we build this Docker image, right? So I actually have got a Docker file over here. It's quite lengthy, but we are essentially using the NVIDIA CUDA Delve development image that we update. We perform a series of installations of some requirements in order to build things like AutoGPT, as well as the nightly version of TensorFlow, because I'm using CUDA 12.1. Copy requirements, copy download model, copy download instructor. Then we start to run the installation of the pip requirements. Then we install Torch, which has got which is a nightly build. Then we install AutoGPT. AutoGPTQ from the GitHub repo that we run. We create the models directory and we download the Manticore model from Hugging Face. Now this download model.py is essentially from Ubuga, right, which has got a web generation UI. Then we copy the environment variables and we initiate the download instructor.py. So download instructor.py, what it essentially does is that it helps to download the Hugging Face models, the Hugging Face instruct models into the Docker image, right? So this allows us to have a Docker image, although it's very, very large, but makes it very, very portable. Then add the everything into the application, then we have a command to actually start the container. So for the front end, not too familiar with Next.js yet, still picking that up, but something that we can, most of the information is actually inside the pages public index.js folder. And from a Docker file, it's really, really simple. We just use the Alpine node image, npm install the dependencies, then we expose port 3000 and npm run. So this is basically the code. It's posted on GitHub. Feel free to download, use, replicate, whatever. Right. So lastly, I'd like to shout out a couple of people. First one to Nutanix for compute and a simple cloud platform for me to actually perform my learnings on. The blog for providing quantized models and for all the advice and help they has provided over the weekend. Ivan Martinez for private GPT and installing the urgency to start building. So Menlo Park Lab, who actually used Ivan Martinez's private GPT repo and actually wrapped it in Fast API. AutoGPTQ and LangChain to make all this happen. So thank you for listening and thank you for watching, everyone. Cheers.